Dallas, Texas, supporting the General-Purpose Amplifiers team, and I'm joined by my colleague, Jerry Madalvanos, an applications engineer also supporting the General-Purpose Amplifiers product line. And as a bit of an agenda for the rest of the 30-minute webinar, I'll be presenting for the first 20 minutes and hand the presentation over to Jerry for the last 10 minutes of this session. And I'll start by talking about what Texas Instruments at a high level has been investing in terms of process technology and manufacturing, and then how that translates into the innovative technologies and industry-leading small-size packages that we're offering within the general-purpose amplifier portfolio. I'll then give an update on the new products released in the last 3 years from the low voltage, high voltage, and standard amplifier product categories within general-purpose amplifiers. And then for the last 10 minutes, I'll hand the presentation over to Jerry, who will give a brief introduction and live demo to show you how to get up and running with the brand new pspice-for-ti simulation software. Now, to provide a little bit of a background for Texas Instruments amplifier portfolio, we have a very broad and differentiated portfolio consisting of linear amplifiers and switching amplifiers. Switching amplifiers includes low power audio and mid power audio amplifiers. And from linear amplifiers, we have RF amplifiers, high speed amplifiers, comparators, precision, and general purpose amplifiers. And for the rest of this presentation and the new products I'll be showcasing will all come from the general purpose amplifiers product category here. And these are devices with about 1 millivolt of offset voltage and above and less than 50 megahertz of gain bandwidth. These are devices that are designed for applications with cost-sensitive targets, any multi-sourcing or requirements in any of your applications, and any projects with requirements for a small footprint or small PCB size. Our target markets are industrial, automotive, consumer, and commercial equipment. And if you have any of the interest in the other product categories, please stay updated with the new product updates that you can find at ti.com/NPU. Now, you may be familiar with this already, but Texas Instruments is very invested in our process technology and manufacturing capabilities. TI was the first company to develop a 300 millimeter wafer fab dedicated to just analog and power products. And since then, we've doubled down that investment by introducing a new fab and retrofitting existing fabs to support 300 millimeter capacity. This allows us in general purpose amplifiers, a product category that ships over 2 billion units a year, to increase our manufacturing throughput over tenfold by moving previous generation products from smaller wafer sizes onto the newest process technologies that are supported on 300 millimeter wafer designs. This also allows us to innovate in some other vectors and includes integrating some features that become standard in our new product releases and introduce new packages to the market. One of those features that you'll find in all the products that I'll be introducing today are EMI hardened inputs. These are simply EMI filters that you can find on the input, power supply, and output pins for all the devices that I'll be showcasing. The EMI-RR rejection ratio curves on the bottom right will be included in the data sheets for all these devices. And these are integration that helps you prevent that high frequency switching distortion that gets introduced by things like cell phones that you can find near previous generation products. The other vector that we innovate on with our investment in manufacturing and process technology is the packages that we offer as a general purpose amplifiers team. On the bottom right, you can see sort of the roadmap of where we have been, where the whole market has been, and really where the future is headed. Whenever we release a device, a general purpose amplifier core release, our strategy is to release all these different package options to allow you to either multi-source an existing footprint, because all too often you find a device that fits your specification requirements but doesn't fit the solder footprint you have today, or introduce small sized options that allows you to save some PCB space. For single channels, you'll find SOT23 and SC70 as industry standard packages, but we're also introducing the brand new X2 SON 0.8 of a millimeter by 0.8 of a millimeter. This is the industry's smallest op-amp package. For dual channel, we have the SOIC, TSSOP, and VSSOP, sometimes called MSOP packages, which are industry standard, but we're introducing a brand new 8-pin SOT23 device, which is the same pitch as the TSSOP and VSSOP, but a little bit thinner in its size, as well as a 2x2 WSON and a 2x1.5 10-pin X2 QFN package. For quad channels, you'll find SOIC-14 and TSSOP-14, the industry standards, but a brand new 14-pin SOT-23 with a smaller dimensions, as well as for leadless projects, WQFN 3x3mm and X2 QFN a 2x2mm, which is the industry's smallest quad channel amplifier. And for any of the industrial applications, one thing we really think is the future for packaging is this 8-pin SOT-23 package. The SOIC, TSSOP, VSSOP packages aren't going anywhere, and they're very popular, but this package allows you to maintain that 0.65mm pin pitch by keeping 8 pins on a single channel, what was traditionally a single channel 5-pin device. We just stick 8 pins on, and now you're getting a 2-channel amplifier for the space savings of what was only a 1-channel amplifier. And then also with the same pin pitch, you're able to multi-source with an adjusted footprint layout, and we have hyperlinks here to show you how to do that. Here's a package menu of all the different packages that we offer within the portfolio of new releases that I'll be showcasing from smallest to largest. And I wanted to call out the column denoting shutdown functionality. You'll see that there's a checkbox for single, dual, and quad channel shutdown functionality. Now, within the market today, I estimate that about only 10% of devices have shutdown capability. And this is where you take 1 extra pin for single channels or 2 extra pins for dual or quad channel, and you have an enable logic pin that allows you to turn the amplifier on or off without disconnecting the supply voltage. On the bottom, you see a side-by-side comparison of a device that has this shutdown functionality, the TLV-9000X, versus the previous generation TLV-313. When shutdown is enabled, you're only consuming 500 nanoamps versus a continuous 65 microamps. So with a duty cycle of 10%, you're able to save and extend your battery life 10 times by going from 60 microamps to only 6 microamps. So for any application that is battery powered or power saving conscious, and you're only taking a few samples every few milliseconds, shutdown functionality is something you can find in all the catalog product releases I'll be showcasing. Now, as an overview for the rest of the new products that I'll be showcasing, we have these separated into low voltage, high voltage, and standard amplifiers. Low voltage devices are ones where the single supply voltage is about 7 volts or below. High voltage, commonly released on a 16-volt process node and 40-volt process node, and standard amplifiers. These are the ones that op-amp enthusiasts might recognize some of these names. I won't go into too much detail on this particular slide, but the green color for the products denotes what's fully released today, and the red denoting what's either sampling or some of the packages are released and we are sampling the others. For the low voltage, you'll see TLV-90 is a very popular naming convention, and we're just adjusting the bandwidth of these different devices. At the bottom, you'll see OPA X375. This is a good time to point out that the OPA prefix devices typically have that higher end and more robust design, where TLV op-amps are really optimized for cost-sensitive applications. In the high voltage, you'll see 40-volt and 16-volt releases, both from 1 megahertz and 3 to 5 megahertz bandwidth options. And then from standard portfolio, we've refreshed the popular LM358 family of devices on a 5-volt CMOS process technology, as well as below a 36-volt bipolar process technology. And we're sampling the TL0XXH family, which is a popular JFET input architecture device. Now, diving into the catalog low voltage devices, at the top half, we have what we consider the general go-to devices, and the bottom half, the differentiated. On the left side of the arrows are the previous generation products that you may be familiar with or using today. And on the right side are the newest releases within the last 1 to 3 years. At the top, TLV-9000X, the 1 megahertz release. TLV-906X below that, a 10 megahertz release, both rail-to-rail input and output, low offset voltage, and includes those EMI hardened inputs. From the low power family, the TLV-904X is a new 350 kilohertz release, so in that micro power range with only 10 microamps. And then for high slew rate, we offer the TLV-905X, a 15 volt per microsecond op-amp with only 330 microamps of quiescent current. And for low noise, OPA X375 and TLV-6740X. Diving into the TLV906X, you might notice that image of the industry's smallest op amp. That's a regular finger. It's a 0.8 by 0.8 millimeter package, 5-pin. And this TLV906X device will be released in all of those different packages that I showcased earlier. But this is a 10 megahertz rail-to-rail input-output device, 1.8 volt to 5.5 volt supply. It has an extended temperature range of -40 to 125 C. And the different packages that we offer are included for this device as well. The TLV904X is that low power device that I mentioned. And one thing very interesting about this device is the ability to be supplied from 1.2 volts. So the recommended and specified supply voltage extends all the way down to 1.2 volts to give you some additional power savings if you have some sort of coin cell battery or powered from a digital I/O rail. Also, you could take advantage of the shutdown functionality to save on power consumption, but also extend your gain bandwidth product with 350 kilohertz of unity gain bandwidth. And the TLV905X will be the last device that I mentioned from the low voltage portfolio, the 5 megahertz option. This one actually has a rather high slew rate with 15 volts per microsecond for only 330 microamps of quiescent current. And we do this by actually integrating some features that we call slew boost technology. So on the right side, you see the traditional input and output stages of an op amp, where the first stage, the transconductance converts a differential voltage into a current. The second stage gains that signal and charges your Miller compensation capacitor. In previous generations, you can only have a slew rate or output voltage change as fast as you can charge your Miller compensation capacitor. So what we do is integrate a current source with a detection switch that allows you to source more current and output and change your voltage faster. So on the bottom left, you can see a side-by-side comparison of a last generation device versus a slew boosted device. And on the bottom right, see the comparison, how you're getting 15 volts per microsecond at only 330 microamps of quiescent current. And then from the high voltage portfolio, again, a roadmap slide denoting what is in production and what is sampling today. On the left side are the last generation products you may be using today. And on the right side, we have a column for 1 megahertz releases and 3 to 5 megahertz releases. And at the top row, we have the OPA devices, the more higher end rail-to-rail input and output 40 volt devices, something rather unique to the general purpose space, rail-to-rail inputs for a 40 volt node. And then the TLV930X and 935X below. These are the more cost optimized 40 volt releases, 1 megahertz and 3.5 megahertz with a little bit relaxed offset voltages and into V minus common mode range, great for multi-sourcing applications. And at the bottom, a 16 volt node, TLV910X and TLV915X. You can find all these devices online on ti.com today, but I'll jump into the OPA X990 device first. This is the 1 megahertz rail-to-rail input and output device, CMOS architecture, and it has what we call MUX-friendly inputs. And I'll describe that technology in just a little bit, but this can be supplied from 2.7 to 40 volts, so great for simplifying your bill of materials and using one device as a Swiss Army knife to fit a lot of different applications, as it can fit high side current sensing, low side current sensing, etc. Now, this device also has very high output current at 80 milliamps and a high slew rate of 4.5 volts per microsecond for a 1 megahertz device. And as I mentioned, that MUX-friendly input architecture. So in a traditional high voltage CMOS device, you have these back-to-back diodes you'd see on the right side, which are ESD protection diodes on your inputs. And in your apps max value of your data sheet, you can only have a differential voltage of 0.7 volts or one diode drop on your input pins, meaning you have to use a closed loop configuration. With the MUX-friendly devices, you're able to extend and pull apart your inputs because of the way we handle our ESD protection today, and have a differential voltage extending the full range of your supply voltage. So you can have 0 volts and 40 volts on your input pairs as long as you're supplied from 0 to 40 volts. And this allows you to settle your signals much faster. So you can imagine using a MUX before this, having a step response of a high voltage change. And on the bottom left, you see a side-by-side comparison or overlaid comparison, I should say, of a device with MUX-friendly inputs versus one without, and how you can settle much faster. And again, in the downloadable slides, we have more information hyperlinked at the bottom if you're interested in reading more about MUX-friendly input architectures. And then lastly, from high voltage, the OPA X991. Similar design, but a little bit higher gain bandwidth product at 4.5 megahertz. And we've actually improved the offset voltage on this one. So without any trimming or design tricks, we're able to get 750 microvolts max guaranteed, a very low offset drift, 10 nanovolts per root hertz, so rather good noise and high output current. Again, still slew boosted to 22 volts per microsecond and a high cap load drive. So this is the OPA X991. The X for all these devices indicating single, dual, or quad channel package options. And then lastly, the third product category that I'll go into is the standard amplifier refresh. So if you're familiar with any general purpose amplifiers, it's probably the ones on the left side of the screen, the LM358 and 324 dual and quad packages, and then the wider temperature LM2904 and 2902, the -40 to 125 devices. And then below that, the TL07, 8, and 6X devices, popular JFET high voltage devices. We've refreshed these different devices into the LM3XXLV devices, those low voltage CMOS devices that I mentioned, as well as the B versions. If there's one thing to remember B is better. And if you're looking to qualify or refresh an existing project using any of the popular commoditized amplifiers, please take a look at the new B versions that we're offering. And then from the JFET devices, the new H versions utilize that 300 millimeter process and design and process improvements. Here's a side-by-side comparison of the popular LM358 and 2904. So you see the legacy portfolio on the top left, just different temperature grades of a similar design have been refreshed to a 36 volt node and a 5.5 volt node and extended the temperature ranges a bit. And then on the comparison table below, we have some different performance specifications, and the LM358, LM358A, which was the more premium, lower offset version, and the LM2904 compared to the blue high voltage releases and the red low voltage release. You can see we've extended some of the temperature ranges, made 3 millivolt offset standard for all the new releases. So there's no longer a premium model for a low offset. 3 millivolts is now standard for other releases. Gain bandwidth has been increased. The ESD rating has been increased to 2 kV human body model. And we've integrated those EMI filters. And now we're releasing more package options than we had previously. And a similar strategy for the JFET architecture, TL06X, TL07X, and TL08X. These are the H version refreshes that you'll find online soon, and the voltage range has been extended, so now you can be supplied from lower voltages and still 36 volts on the high end. Offset voltage has been significantly improved from the previous generations. We've improved the bias current as well, and the ESD ratings and temperature ratings for all these products have been improved. So the performance for all of these standard amplifier products has been improved upon. The supply capability from that 300 millimeter wafer manufacturing, and then also the pricing that you'll see directly from ti.com has been improved in all these refreshes. So again, if you're using any of these products today of the previous generation and you have a redesign or new project, I highly recommend that you check out some of the new releases, contact your local TI representative, and see what we can do for you. And for the last 10 minutes of this session, I will transition the presentation over to Jerry Montalbanos, who's going to give us a brief introduction and get started guide to using the brand new pspice-for-ti simulation software.
All right. Hello, everybody. My name is Jerry Montalbanos. I'm an applications engineer in the General-Purpose Amplifiers team, and I'll be showing you the pspice-for-ti new simulation software that we've released. We're going to do a little bit of an introduction, and then I'll transition to a live demo. So first things first, we're going to go over the benefits of pspice-for-ti. We're going to go over how to download it, and then we're going to create and run a project. So the benefit is we built our simulator in a very familiar setting. For a lot of people, OrCAD Capture is a very industry standard software that you already know and love. And we've integrated TI's library with that to bring you a streamlined process to simulate our circuits in your design. We give a full featured simulator with Monte Carlo simulations, worst case simulations, thermal simulations. There's a suite of training videos with both introduction and advanced topics, There's integration with TI.com, and this is a really big one, that there's an integrated library with thousands of built-in models that automatically synchronize with TI.com. There's E2E forum support, so you can go online to the E2E forums and ask questions about pspice-for-ti or your circuit that you've built. There's the ability to work offline, and you can use unlimited markers for TI models. There is a 3-marker limit for non-TI models, but you can pay to upgrade to unlock the marker limit. But as long as you stick with the TI models, no marker limit. Now, here's the download link and the link to the tutorial videos. And how you're going to download pspice-for-ti, you're going to navigate to the download link linked here and in the previous slide. You're going to request it. You're going to log into your MyTI account, fill out the required information, and your approval can be immediate, but it may take up to 48 hours, excluding weekends. And then you're going to follow the instructions in the email to download pspice-for-ti. Now in the live demo, we're going to create a project. We're going to build a simple circuit. We're going to create and run a simulation profile, and we're going to view the results and export it as a zip file. So transitioning over to pspice-for-ti, we're going to go over here to File, New, Project. The project that we're going to build is from the Analog Engineers Circuit Cookbook. We're going to go to the Inverting Summer circuit, and we're going to build this today. So we're going to call this Inverting Summer. We're going to create a blank project. And first things first, we're going to place our amp, so TLV170. Now, before, you would have to go to ti.com, find the amp, download the simulation file, and import it into your simulator. Here, with the curated library, you just search it, and it's natively in pspice part search. So you're going to double-click, click once to place it in the schematic. Now we need our passives, so we'll search up resistor. We'll find the general resistor, place 3 of these. Now we need our supply rails, VDC, and a lot of these are the same names of the components that you already know from OrCAD Capture. So place our supply rails. Now we need our input. Depending on what simulation you're going to be running, you need to provide a different input voltage. So some simulators allow you to change your voltage source. pspice has broken it down into separate voltage sources. So V-sine gives you a sinusoidal transient voltage source, whereas VAC will allow you to run AC simulation. So now we have the sources. Now let's place our grounds. We're going to press G to place grounds, and then we're going to use 0 capstan, which is our DC ground. And now let's wire up the circuit. So press W to enter the wire tool. Connect the circuit as seen in the cookbook. And then I'm going to add some extra wires onto the pins for VCC, VEE, and to the top of these sources as well. This is so that when we go to set net aliases, you can't set those to a pin, you have to set those to a wire. So now doing that, I'm going to label the output Vout. We're going to set up VEE, VCC, and then VIN2 and VN1. Let's clear this up a little bit, it's a little cluttered. All right, now we assign values to the components. So double click the value that you want to change and just type in the value. Generally, it automatically knows if it's going to be ohms. You don't really have to specify 20K. This is 5 volts. 5 volts. And now setting up our inputs. So our input signals are going to be a 5-volt peak-to-peak sine wave at 1K hertz, a 250 or a 0.5 millivolt peak-to-peak sine wave at 10K hertz, and we should get this as the output. So they're both centered around 0, so our V offset is 0. Our amplitude is, this is VN2, so this is 250 millivolts. The frequency is 10K. And then the AC value we don't have to assign because we're not doing it in AC simulation. So the offset is 0. The amplitude is 2.5 volts. And the frequency here is 1K. So now what we're going to do is we're going to set up our simulation profile, and I'll show you how to place those markers as well. So we're going to go up here to create a new simulation profile. We're going to call this transient. Click create. Then the default settings are pretty standard. They're basically what we're going to do. And the run-to time, I'm going to choose 3 milliseconds so that we can get 3 periods of our slowest input signal. So generate the simulation file, and we're going to place voltage markers. So we're going to look at V out, we're going to look at VN2 and VN1. It's important to place the voltage markers after you create the simulation profile because otherwise it'll clear it when you create a new simulation profile because it saves the markers between simulations. Now we're going to go up here to run, and the pspice simulation window will pop up here. All right, this is a little bit cluttered, and we can separate these by right-clicking, adding a couple plots, and you can actually just copy-paste the traces and put them onto the other plots. So looks like it matches pretty well with our expected results. Now, if it didn't, say there was some mistake in how we built the circuit or we were missing a value or something, if you wanted to troubleshoot it or you wanted to send it to a field apps engineer or you wanted to send it to an engineer at TI, you can very easily export the project with your simulation. First, you have to click the .dsn file up here to change the file setting. Then go to File, go to Archive Project, and then you're going to include the library files, the test bench, your simulation profile, and reference project. If you imported anything, this will include it in there. Then you're going to create a single archive file. It creates a zip file with the default name being the project name and then a date code, so 2029-17 and the time. And you can change this to be whatever you want. Send that zip file, and then your field apps engineer or your TI engineer will have everything that you've done, all the simulation profile, the markers, etc. And it makes it a lot easier to troubleshoot your design. So that's what I had for today for the demo. You can visit ti.com/npu to find these slides and to find a recording of this presentation. And I'll pass it back over to Emily.
Thank you, everyone, for joining. Like they said, the presentation, the archived webinar will be on ti.com/npu within the next few hours. And we hope to see you next week for our next webinar. Bye.
Thank you.